Okay, thank you. Okay, then let's start. Well, this time it's a bit more theoretical, and really we are getting to the part where we will have an implementation. So today, I guess in the evening, I would share the code, the shader toy code. I would provide a version that is basically a reference, which is everything that you need is implemented there. And I'll provide a version that's stripped of some code, let's say of the path tracing code. So you can try to implement a very simple unidirectional estimator. So that's the only thing, the boilerplate is done, and you just have to implement the estimator in an iterative way. And you can obviously you'll be able to see the reference code. So if you need to, if you don't, you can just try to implement it by yourself, etc. Okay, then let's start with today's topic, which is really the rendering equation would be formulated in a operator form. So this is just for conciseness. Then the measurement equation would be studied. And finally, we'll see, okay, different ways to rewrite this measurement equation, which would lead to a formulation you can use to construct bidirectional path tracing estimators. Okay, so as mentioned, the motivation here would be to basically get something more general, and that would be based on the measurement equation. So you can see this is something from I think chapter 2. We have the measurement equation introduced. So you have the flux over some set W and some set of directions omega. So W here is a set of points, and this is points on your sensor, and these are directions from which your sensor can accumulate light. So imagine a camera with an aperture where these directions really show you, okay, from which directions you can get any light from that aperture. Okay, and you can write this measurement equation as a double integral, so over the points of the sensor and over the directions from which it can get any light. And you can integrate the radiance multiplied by the cosine there. So everything here should be clear, and you can make this somewhat artificially more general by making the integration of all scene surfaces. So you assume your sensor is part of these scene surfaces. You can assume it to be transparent, so it doesn't interact with light. It can just measure it, let's say, and over all possible directions. And then you can filter out these two sets by using an indicator function WE. This is what we work with. So this is one of the standard forms that you see of the measurement equation, and that you should have seen in the book. Questions on that? Okay, if there are no more questions on that, let's see several different variants of the rendering equation. So this is really something like a review. We have the rendering equation with respect to excitant radiance, and you could write it in this manner, where you have incident radiance here, or you could rewrite the incident radiance as excitant radiance by using the energy conservation along light ray. So the energy light arriving at X from the direction omega is the same as the energy leaving the intersection along this direction from X. So this is some other point on the scene surfaces towards the negative direction. So pretty straightforward. And you can obviously do this for the other formulation. So you can flip this around. This could be a low and this could be a high. So it shouldn't be any issue. So this is with respect to excitant radiance. This should, yeah, so you can obviously rewrite the equation. This equation not with respect to solid angle and integration over the hemisphere, but with respect to integration over all scene surfaces, so over area. And then you have the relationship between the differential solid angle and differential area that gives you a term like this. You also have the cosine here, and if you combine these two, you get you can absorb them in some function, geometric function, something like this. Then your equation looks like that. So this is for the area formulation. Obviously, this is something we've seen in the second chapter. This is just a review, just to remind you, okay, what were the formulations, then you can go to some other formulations where, okay, here the radiance was exitant, so from x traveling in direction omega O. And you can flip this around and say, okay, I want radiance arriving at x0 from some direction minus omega O, and then you get a equation that is in some sense in the opposite direction. You have your arrows here. So these are different functions. This Li is different than the LO. You can transform between the two. Yeah, and you can and you can do the same thing for the surface area. So this was with respect to solid angle and surface area. So in total, you get 4 equations. The 2 variants for surface area or solid angle and the 2 variants for excitant radiance or incident radiance. And you can write 4 such equations also for the importance function, which would arise from this WE. So let's look at this. So we have the measurement equation, and then we have the filtering function WE. But thinking of this function as some virtual radiance emittance function, you can write a similar form as in the rendering equation. You can write a similar form that we call the importance equation, which propagates some quantity code importance. So it's similar to radiance. The only difference between these two, so between this equation, let's say, and this equation, is that here you have the GRDF, you have the 2 arguments. First, you have omega I, so the incident, let's say, direction, and then the outgoing direction. Here, these are simply flipped. So that's the major difference, and obviously we have replaced L with W everywhere here. And you can obviously make the 4 variants that we saw above for the importance equation, the same conservation of importance along rays in vacuum holds as for radiance. So it's almost the same thing. Questions on that? No questions, then we'll continue with the flux formulation. So we saw the measurement equation, and you actually rewrite this measurement equation in several different ways. What we saw previously was, okay, you have some filtering function WE here, and you have the incident radiance here. You can also decide, okay, I will use the observation of light along the ray to rewrite Li as LO. Then you can have both functions have the same direction in some sense, but now the arguments do not match these arguments. Now, if you want the arguments to always match, then you can also flip the direction here, but you also need to flip the direction here. So this is valid. This is the same as this, just written in a different way. So they compute the exactly same thing. You can also decide to, okay, I will drop the E here, so that would not be the emittance function, and I would just get my generated function from this. And then you can couple these 2 functions, W and L, so the importance function and the radiance function. And once again, you get the exactly same result. So you can mix and match these as you like. Questions on that? No questions? Then let's continue on to the operator formulation. So what would be an operator here? I'll just talk about the specific case. I will not discuss operators in the general settings in mathematics. Think of it as a higher order function in programming. So we have a higher order function t, you give it some other function f, and it produces you a new function g. So how does this work? Well, you have t of f, which is a function. So this whole thing is a function, so you can give it some argument, something like this, and this produces you a new function. Let's see an example of that. So let's say your function f of x returns x squared. Now let's say you say, okay, my operator that takes some function, he doesn't care what function it is, it makes it to the power of 3. Then if you combine t of f, so then you have x squared, and then to the power of 3 you get x to the power of 6. I think this is pretty straightforward. You can also think of T as a kind of a macro in programming, so just substituting things. Yeah. Why would we need something like this? Well, just to be more concise, to be able to not write something as long, but something a lot shorter. So how does this work? Well, we have the rendering equation here, and we want to write this in a shorter manner. Well, we'll say, okay, we provide an operator T that takes this function L and produces this expression. So then I can write this more concisely in this form. So this TL is just, think of it as a macro expansion that expands to this thing. And then we can drop the arguments, because you can see the arguments everywhere are the same. We can drop them and we can write this equation in this form. Then we can just, using mathematics, just, okay, move this to this side. Then this is the identity operator, so it's like L was multiplied by this. The identity operator of a function gives you the function itself. And the formal solution of this is just I minus t to the power minus 1. This would be the solution. Now, what does this mean? It's some kind of inverse of an operator. And the inverse of an operator, at least in this case, would be given by just an infinite sum of the operator applied to the power of k. So what would that mean? Here's an example. Let's say that you want to apply t to the power of 3 to f, which is simply applying t 3 times to f. So the first time you get some function f1 by applying it once, then you take that function f1, you apply t on it, you get f2, then you apply once again on this new function, you apply this operator, so you get t3. If we go back to our example here, so that would be, applying this 3 times would be equivalent to applying an operator to the power of, I guess, 27 here. Questions on that? Okay, if there are no questions, then we can continue with this and see, okay, how does the solution now of our rendering equation look like? Because this would give us the solution, so this is simply an infinite sum. And we can look at, okay, what are the terms in this thing? Well, the first term is t to the power of 0 LE, then plus t to the power of 1 LE, plus t to the power of 2 LE, etc. And t to the power of 0 is simply the identity operator, which doesn't change the function, so it just gives you the emitted radiance function. Now, what is TL? E, so the one application of that, well, we define it above, we define it right here with respect to an arbitrary function. So the only difference here is that this is L, which we don't know, but LE we know. So we can write simply by expansion this thing. Then we can continue on to rewrite this, let's say, in an area formulation. We can also consider, okay, what's t squared LE? Well, t squared LE is simply the light arriving from 2 bounces away, and it's simply applying the integral 2 times. So you can see, okay, I substituted that, and I have this. Then I expand this part according to this rule. I get 2 integrals, and in the general case, if you have k bounces away, this is your term t to the power of k LE, and this is simply a product of the GRDFs along the path, the geometric terms, and the visibility terms. And then at the very end, you have your light source. So just imagine creating a path from your, let's say, sensor. You pick some points on your scene, you connect the points, you get a path that ends up in a light source here. Questions on that? I want to maybe show you some, let me see, do I have this? Yeah. Yeah,
I have a question actually.
Yeah.
The book mentions continuity of the importance function and the radiance function, and I'd like to know if there's a method that we should choose, whether we choose one of the flux formulations, because if that makes a difference because of this
Yeah,
discontinuity.
the flux formulations, the different flux formulations do make a difference. That's how you get bidirectional path tracing. And considering different reformulations of it and constructing estimators for those gives you different probability density functions. Now having different probability density functions is equivalent to having different estimators. So some estimator may be better at something, a different estimator may be better at something different. Now, if you combine all of this, you get something better, let's say. Let me show what I wanted to. Is it here though? Oh, okay, it's here. So what I was talking about, your solution, so the radiance in the scene is a sum of the emitted radiance coming directly at your camera, so primary rays only, one bounce away, you can see it here, two bounces away, three bounces away, and if you sum this, so if you sum this plus this, you get that, if you sum this plus this plus this, you get that, etc. Obviously, in the practical setting, at some point you cannot make an infinite sum. So at some point you say, okay, I stop, and you just cut off the terms after that. So you lose some energy from higher bounces, but obviously you cannot go to infinity. And the assumption is that with enough bounces, the energy becomes smaller and smaller. And you can see here, okay, let's say this is fairly high energy, lower energy, and at some, let's say, T10, then it would be negligible, maybe even less than your quantization for the pixel, so less than 1/256 or whatever. So you cannot even show it on your screen. Questions on that?
I'm gonna reformulate my last question because what I meant by whether the method you choose makes a difference is that the book mentions continuity of the functions.
Yeah. So okay, imagine you're sampling the BSDF. Okay. Now, if you're sampling the BSDF, over your BSDF, you have some light sources, right? You can hit the light source directly, and then you can hit something else that is not a light source. So LE there is technically a discontinuous function, right? If you look from the perspective of the BIDF, let me find it. So if you just look from the perspective of the BIDF, yeah, okay. So let's say you are at this point here, right?
Okay.
And you're looking at from the perspective of your BRDF. So this is your BRDF, and you sample that. So what can happen there? Well, you may hit. Okay, you have some projection of your scene on this hemisphere, right? And the light there, this thing here, would be discontinuous in the sense that, okay, if I'm at the very edge of it, so if I'm at, let's say, if I'm at this edge of the light here, everything's fine. If I'm inside, everything's fine here, but in between this, it is discontinuous, right?
Okay.
So viewed from the perspective of this single point of its hemisphere, this is a discontinuous function. Now I can do something else. I can pick area sampling. Then I sample points here. So I'm looking at the scene from the perspective of the light in some sense. And then this is obviously not discontinuous because my domain is only here. So I cannot even sample a point outside it. So this is continuous with respect to the light, but it's discontinuous, let's say, with respect to the BIDF and the geometry, because you'll see these edges. So does that make sense?
Yeah, it does.
But it's not only
what I've been thinking about is
yeah.
that this chapter this chapter mentions finite elements as a method that can estimate discontinuous. I don't remember if it was radiance or importance, and it mentions path tracing as a method that can sample a discontinuous, like the opposite of finite elements. Maybe I'm mistaken.
No, it's not the opposite. So actually, you can write what you do with Monte Carlo as some kind of implicit finite element method, but that's way beyond the scope of this book. One is not, let's say, more powerful than the other. It's just, let's say, in finite elements, you have the problem of meshing your domain. So you need to subdivide it into some pieces. Then on these pieces, you need to define some basis functions, etc. So we will see that in chapter 6. But generally, if you compare Monte Carlo, so what we'll be doing, to finite elements is a bit more first involved, and second, there are some restrictions and it's not as clean. Like the math is clean, but the implementation is a lot more involved, and handling effects like specularity, etc. is a problem. But it's unrelated to this continuity, discontinuity. You can pick continuous basis functions on your meshing, and then everything would be continuous, etc. But yeah, that's kind of beyond the scope of at least of the current chapter.
Okay then.
Do you have more questions or?
No, that's it.
Okay.
I do have a question.
Yeah.
So I'm confused why at this chapter we've decided to switch over to the flux formulation for the rendering equation.
Well, because okay, I had this previously, but let me actually pull up the previous version. Where is that? So I had that in the motivation of the previous chapter. Yeah, I think that's it. Yeah. So what you want to compute? Let me see. Yeah. What you want to compute at the end of the day, right? Is some value for your pixels. Now, depending on your camera, your virtual camera in the virtual world, you measure different things. So let's say you take a pinhole camera, right? Now, if you take a pinhole camera, you have only one point in some sense where you measure things, but many directions, and that one point is your aperture. And this corresponds to measuring incident irradiance. If you remember irradiance, it's you integrate over solid angle. Now, if, for example, you pick an orthographic camera, now your pixels, like on the virtual film, they have an area, but they consider light from only one direction. So you integrate over some area, but you care only about a single direction. So that's intensity here. So that was irradiance, that's intensity that you measure. Now, if you assume a more realistic camera that has an aperture that's not a single point, so you would have depth of field, etc. with that, and regions of your film that correspond to your pixels that are not non-zero, so they have some area, then you measure radiant flux. So that's why we want to have flux, because for every pixel, we want to compute the flux, let's say. And you can go further and actually measure energy for every pixel. If you want to simulate, let's say, motion blur and exposure, because then you would integrate also over time. Does that answer your question?
Yes, thank you.
Yeah, so for every pixel we want to, here we would assume that for every pixel we want to measure the flux. And to measure the flux, well, you have to integrate out over the region of the pixel. So let's say some small rectangle on your film corresponding to the pixel. So that would be W here. And omega x here would be simply the directions that pass through the aperture. If the direction simply hits something like the inside of your camera, well, we assume no light arrives from there. So that's where this integral comes from, and that's why we'll need it. Basically, that's why we want to compute this and not simply radiance, because we want to integrate radiance over some domains. Yeah. So we go to this part, which is really okay. How do you compute the just radiance? If you want to find this function, you don't know it. So what do you know about your scene? Well, you know the BRDF, you know the geometry. So where is the BRDF? Here's the BRDF. The geometry is implicit here, but if you look at the area formulation, where is the area formulation? yeah, if you look at the area formulation, then your geometry is explicit, so you have it here, and your BRDF is explicit. These things, this you can compute from the geometry, and this you can also compute from the geometry. So given your scene, given your BRDF per every point and whatever in your scene, then the only thing that you need to find out, because this is an unknown function, is also the radiance. So combining the emitted radiance, your BRDF, your scene geometry, and on top of that, the sensors that where you want to measure it, well, you can find your solution. But you still have this unknown. And this unknown can be found simply from the scene geometry and the BRDF, and giving the sources, the light sources. So, and to compute this function L, we use this expansion of, okay, L previously was some kind of recursive equation, so you had L here and you had L in the integral, so the unknown showed on both sides, and that's obviously not very nice for computation. So what you do is you say, okay, let's in some sense take this expression, plug it in here again using that, then plug it again and again, and you get a sum that grows until infinity. So this is really it. This is your sum. And the sum is very, very intuitive. It tells you, okay, where is that? It's around here, I think. It tells you, okay, how much light do you have that arrives from one bounce away, from 2 bounces away, from 3 bounces away, etc. Yeah, so we have really this thing. And you measure, okay, this light, this light, this light, you sum them up and you get a better and better image. So less energy that you've omitted. And these are, so what's the nice thing here? You know LE, you also know these integrals. So you know everything in this integral here. You know the BRDFs, that's given with your scene. You know this because, once again, that's given in your scene. You know your scene geometry, that's given. And you know the sources, so you can compute every, or estimate it numerically. You can estimate every integrals of those numerically. So those are, that's a sum of, where is that? That's a sum of integrals. And by just summing up your estimates, you get an approximation of L, which is really what you want to get any visible image. Yeah, I think we'll, are there questions actually? Okay, if there are no questions, we'll do a 5-minute break, and then we'll continue with the adjoint operators.
Before we do that, just a quick question. When do we stop? Because it's a recursion for that converges to an infinite series. So when do we stop? I heard about Russian roulette, but it's pretty unclear to me.
You're asking when do you? In theory, you do not stop. In theory, you go to infinity.
Yeah, but like.
So what may happen? Even in theory, you may not need to go to infinity. Why? Well, imagine that after n bounces, so imagine a diffuse scene, and after n bounces, all of the energy has been absorbed. So no more energy can pass through that many bounces. It gets attenuated to 0. Then you can just stop at that point. In practice, you say, okay, at some point my energy would be so small that when I show it on my screen, for example, let's say I'm storing my image with 8 bits, then if the error is smaller than the delta between, let's say, 2 gray levels, well, it doesn't make sense to compute it. So you can stop at some point. And in practice, you say, okay, depending on the scene, I can choose some point at which to stop, let's say 10 bounces for a diffuse scene or something like that. And then you stop at that point and you say, okay, that's it. Now, if you want to go higher, so you assume, okay, your scene may have mirrors, which may require, let's say, 100 bounces, but your diffuse materials, they would require only 5 bounces. So in some sense, you want some rays to stop at 100 bounces, others to stop at 5. Well, then you can use Russian roulette. Then you can set the maximum to 100, but Russian roulette would stop most paths that are too dark, that do not contribute much, very early on. So it would be like for diffuse paths, you would get 5 bounces, and for mirror paths, you would get 100 bounces. Does that clarify it?
Yeah, pretty much.
Okay, then we will do a 5-minute break. I'll be back in 39. Yeah. Okay, I'm back. Yeah. So to summarize what I was saying, well, we introduce operators to get something, basically just to get a concise notation, because, well, otherwise you would have to write something like this, something like that. And now we just substitute this. So just think of those as I said, macros or higher order functions. And when you see t to the power of k, that's simply t applied k times. So like here. Okay. Any questions that you thought of during the break? No, then okay. Then now we have the solution for the radians. We know how to write it in terms of integrals. And last chapter we saw how to numerically estimate such integrals, regardless of the dimensionality. So we can continue on to adjoint operators, which would allow us to get formulations from which you can derive bidirectional path tracing. Once again, to get things more concise and not write something tremendously large, we will use an inner product, which in this case would be once again something like a higher order function, where you plug in two functions and it returns you that. So you just substitute this expression with that. And in the general case, you would use, for example, WE here and L here. And as you can see, if you do that, then you get the simply the expression for the flux. And you can get several expressions for flux which are equivalent. So you can use, let's say, just the emitted importance and the radiance. You can use the importance and the emitted radiance. You can use the importance and the radiance, and you can obviously choose them to be incident or excitant, doesn't matter. You just have to match them to have different directions. So a similar thing holds here. So what would we need operators for? Well, we saw how to write the radiance, the excitant radiance, and the rendering equation in terms of through this operator t. Now the question is, do you get different operators when you use, let's say, incident radiance or importance, etc.? And it turns out, yes, you get slightly different operators. So the substitution that you must do is, so your macro looks slightly different. And we will introduce the notion of adjoint operator. So this is simply an operator. Let's say you have an operator t applied to a function f, inner product of those with h. Then an adjoint operator t star, you can simply move that one here, and that would be your adjoint operator. Now, if the adjoint operator is equal to your operator, then it is known as a self-adjoint. And in our case, the operator t, the light transport operator, would be equal to itself adjoint only when your GRDFs are symmetric. So now you can see why symmetry, for example, is very useful, because then you don't have to come up with different expressions here. And what we saw before was, okay, you have this the rendering equation written in operator form, and we'll split this operator, the light transport operator t, into two operators applied one after the other. One is the propagation operator g, and the other is the local scattering operator k. You can read on that in more details in Vich thesis, 4th chapter. So what's really this propagation operator? Well, it gives you what we discussed before. So the radiance conservation along the ray, which basically told you, okay, if let's say I give, just imagine that for the current case that this is radiance, so LO here. So if I give it an excitant radiance function, I can write it as a incident one. So this is simply an operator that turns your incident function into an exitant, or your exitant function into an incident one. And let me show you where that was. Not here. Yeah, so we have this relationship. So what your operator would do would simply take this function and transform it into this one, or take this function and transform it into that one. So that's your propagation operator. What's the next? Yeah, okay, you have that. The local scattering operator is the other part, which is simply adding this integral multiplied by the GRDF and then by this. And if you combine the two parts, if you look at the rendering equation, you can see, okay, here's my rendering equation. Now I can rewrite that thing as this, which is really the propagation operator applied to the incident radiance function. And then the definition of this whole thing is simply your K operator, your local scattering operator applied on your incident radiance to which the propagation operator was applied. And finally, you get obviously your rendering equation. So why did we do this, let's say, mental gymnastics of introducing two operators when we could have done with one? Well, it's because for the other formulations, let's say, of incident radiance and not exitant radiance of the rendering equation, you get a different operator, Ti, which is simply these two flipped around. So T was Kg, and this is Gk, so applied in reverse order. Then if you also want to write the importance equations in terms of operator notation, it turns out that for the exitant importance, you get the adjoint of the incident radiance operator, and for the incident importance equation, you get the adjoint of the exitant operator for radiance. That's why you actually get the, where is that? That's why you need the opposite directions here, this and this. And this is reflected in the operators that you get. So you have a correspondence of adjoint transport of operator for incident importance to exitant radiance, and vice versa for the incident and the exitant radiance and importance. Now, the operator here, what does this operator look like? Well, it's almost the same as the light transport operator, is just that you use an adjoint K operator. What's the adjoint K? It's exactly the same as K applied to some function. It's just in this GRDF, the direction is switched. So we have omega O going in direction omega I, while in the standard, let's say, operator, you have this point. And this follows directly from the fact that, okay, your importance equation has the GRDF flipped. Do I have it here, though? I think I do. Yeah, so you can notice that for your importance equation, the GRDF's arguments are flipped. So we have omega O goes towards omega I, while in the rendering equation, it's vice versa. You have omega I goes towards omega O. Let me find it, yeah. So we have this. So the direction of travel, let's say, of your quantity is reversed. For importance, it travels in the opposite direction of radiance. Yeah, questions on that?
Yeah, just one quick question. In this formulation of the GRDF, is it equal to the other formulation because they're symmetric, or it's not equal because they would be isotropic?
You can for a second, you can forget about this arrow, right? Just forget about the arrow for a second. Now, say that you have x, comma, omega O, comma, omega I. If you flip the two arguments, you get the other thing. So it's the same function. Does that make sense?
It's the same function, but is the result equal or not?
No, but okay, assume, what do you mean is the result equal? What result?
For example, you get an input omega and an output omega. If you flip those, would it be the same thing or not necessarily?
No, it won't be. So that's the point. If your BRDF is not symmetric, then K star is not the same as K. If the BRDF is symmetric, then K star is the same as K. Because if it's symmetric, you can flip these around and get to the original one. So if you can flip these around without the value changing, then everything's fine, and you have a symmetric BRDF, and then it doesn't matter. And then these operators are actually, so this operator is actual to the operator T, to your usual light transport operator. If they are not, then it's not the same. So it does depend on whether your BRDF is symmetric. If it's not symmetric, then there's a difference. If it's symmetric, then there's no difference whatsoever. In the book, so if you look at the book, they all the time, I believe, they consider only symmetric BRDFs, which in the general case is not true. That's why that's the reason I have these G and K here, like in which thesis, because in the book they don't have it, because they assume, okay, everything's symmetric, but that's not true in general. Even for refraction, it's not true. So even for the very simple BRDFs, it's not true. Questions on that?
Yeah, it's fine, thanks.
Okay, so let's get to the last part of this, which is, yeah, we'll skip the GRDF because, well, it's not very useful. At least what you can say about it is it's really the kernel of the solution operator and blah, 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 but you won't really have any use of that, at least in my opinion. So I think we can just skip it. It doesn't say anything new. So everything that you need, you have it here. And the GRDF is simply the kernel of, where is that? Of this thing, of the solution operator. So not a very interesting thing. I don't know why it's in the book. No idea. Yeah. So let's go to let's go to bidirectional path tracing. So now, why did we need all of this extra baggage of adjoint operators and whatever? Well, it's so we can write the measurement equation in various forms, and by writing the measurement equation in various forms, you can get different estimators, and get, let's say, a large enough collection of those. Well, you can take them, and some of those are good at something, others are good at other things, and you can combine them, and that's generally what you call bidirectional path tracing. So okay, assume that you have your measurement equation with immediate incident importance and exitant radiance. So you can use the rendering equation on that, the operator formulation, to write this. Then you can expand once more. You can write that. Then you can split them due to the linearity of the sum. So these are simply integrands, and you can split them, and you get 3 terms. And now you can use the what we saw for the adjoint just to move these here. So now this thing and this thing, they're equivalent theoretically. They are not equivalent in practice. So when you try to implement an estimator for that. So one thing would be, for example, this thing would be, let's say you shoot based on the BRDF, you get until somewhere, and then you hope you hit a light or something like that. Now you can have the opposite thing. You can shoot your rays from the light and then connect to the camera. And you can, in general, you can, let's say, start with a path of 5 bounces from the camera, let's say 4 bounces from the light, and then connect these 2 paths. So that's a possibility. And by connecting all paths, by let's say you have various ways to construct such paths where you have, okay, 1 bounce, 2 bounces, 3 bounces, etc. You get different estimators. And to illustrate exactly what I mean, let me find the some illustration, I guess. Just a second. And if you have any questions, yeah, feel free to ask while I look for this thing. I think here. Maybe. No. Yeah, okay. Here's, I guess, and you can, I think you can find a similar drawing in PBRT. So your typical unidirectional path tracing, you start from your eye, you shoot your ray, you hit something. Let's say you sample the BSDF, you continue, you sample the BSDF, you continue, and you hope that you hit a light source. So that's one possible solution. And what does this correspond to? Well, it corresponds to something like that, to an expansion like this. Now say you want something different. You want to shoot from the, once again, from your sensor, sample based on the BSDF, continue, etc. Now you can see one path here if you connect directly to the light, and a second path here if you connect directly to the light. So what is this? What does this correspond to? Oh, something like where is that? Something like this. And you can do the same thing over and over. So you can make longer paths from the light and shorter paths from the eye. The only thing that you need to care about is that you always, when you produce your estimators, you always combine the same path lengths. So when you have different formulations for a similar path length, so let's say this and this, you combine only these two, because only these two correspond to the term, to the first term. So you cannot take a path of length 3 and combine it with a path of length 1 in your estimator. Why is this? Well, let's see the solution. Yeah, so you have this solution here, and obviously your sum is over different dimensional integral. So you cannot have an estimator from a d-dimensional integral and then for a k-dimensional integral and try to use it in both. It doesn't work like that. At least the numerics don't work like that. And in the book, at least here, you have a good illustration. So you can do an expansion of that, of your flux, in many different ways. So for example, you can pick this, let's say this, and this. That's one possible expansion. So that's one possible estimator. Or you can do this, this, and this. And that's how you get different strategies. So here, you can write only one estimator for that. For the second, let's say, for the first bounce, you can write two estimators. And you can take these two estimators and then combine them with multiple importance sampling. Now, on the next bounce, you can combine these three estimators using multiple importance sampling, then these four estimators with multiple importance sampling, etc. Questions on that? Okay, if the don't look at that part there. Let's say their figures are misleading, and the interpretation they give here. So it's a bit that part is not nice in the book, like the physical interpretation here that goes all the way to taxonomy. Forget about the path formulation. We won't care about that, at least until we get to metropolis light transport. Questions? I think this concludes it. I can give if there are people that have trouble with the integrals, I can give a discrete analogy, but that's only if you need it. So questions? Does anybody need a discrete analogy for the, let's say, rendering equation, etc.?
I don't need an analogy, but what is the paper with that figure 4.4 that you showed us from some paper with the diagrams for the different? Yeah. What is that?
This is
I like
Ilyan Georgiev's thesis. Let me find it.
Thank you.
But you can find an even better diagram of this, I think, in PBRT.
Okay, I'll check it out. Thanks.
Just the bidirectional path tracing part. Let me, yeah. Here you go. But again, you probably want to see PBIT for an even better diagram there, a better figure.
Okay.
The basic idea is that what you have here drawn in terms of, you know, just some pictures is really what you have here in terms of, let's actually go even here in terms of different strategies. So those would be, let's say this would be a path of length 1, a path of length 2, path of length 3, the different strategies, and here, what you saw here are paths of length 3, for example. So you see this strategy, you see this strategy, and you see this strategy, right? And is there a fourth strategy? And you can, where is that? And you can see the different strategies here that correspond to those. Does that make sense?
Yeah, thank you.
So if you take 4 bounces, you get even more strategies, etc. So it just, okay, how do you connect things in some sense? And these are different estimators, so they're good at different things, and you can combine all of those with multiple importance handling. So yeah, what was I about to say? Yeah, so the code is ready. I guess I'll provide it after the second meeting. I would just post it on, I guess, in light transport answers. And yeah, you have 2 versions. One is the reference, so everything's implemented that you need there, and the other is a slightly stripped version where you would have to implement an estimator, a unidirectional estimator, so very simple, and basically to connect it to the theory. I'll try to put some comments in there. It's not like this is not like a mandatory exercise or whatever. It's just something you can try to do. Yeah. If there are no questions, I think we can conclude the meeting. Thank you for your attention. And yeah.
Thank you.